Hi, my name is Matthew, and this is my RISC project, Too Hot to Handle, Latent Space Safety from RGB and Heat Sensing. For our motivation, we consider the following scenario. Imagine you are preparing toast on a hot pan. However, you have no indication of whether this toast is hot or not. From just RGB input, or what we can see with our eyes, it is not immediately clear to us that the toast is burning or is preparing well. If we continue with the assumption that the toast is preparing well, we might end up with a policy that takes us to a burnt piece of toast. A logical question one might ask in this scenario is the toast hot? If one can reason about the toast temperature, it becomes easy for a human to plan out the next sequence of actions that will allow them to end up with a nicely prepared piece of toast. Given our goal, a logical next question to ask is, how can we define failure? For the toast preparation scenario, for example, how can the robot learn to model failure qualitatively through quantitative means? HJ reachability is a control theoretic framework that gives us safety guarantees for both linear and nonlinear systems. The idea is to compute a value function, V of S, that captures how safe a state is, considering worst-case disturbances or actions. The first equation that you see on the screen is the classical fixed-point Bellman equation used in reachability. We take the minimum between the immediate cost, L of S, which penalizes being in unsafe states, and the maximum over future values after taking any action. This inner max represents the worst-case dynamics. The second equation is a discounted version of this first equation, introduced by Jaime Faizak. Adding the discount factor gamma turns the original fixed-point equation into a contraction mapping. This makes it easier to solve iteratively and enables stable approximations using tools like deep reinforcement learning. The key point is that both versions of the equation allow us to derive safe policies by optimizing over worst-case scenarios, and the discounted version makes it feasible to scale up using neural networks. During deployment, we can use the value function v to define a Q function and use it to find actions below a risk threshold. If the nominal policy's action is safe, we can take it. If not, we just override it with the safest action available. This gives us a simple safety filter that provides what is known as a switching control. However, a key downside of most HA reachability methods to date is that they typically require explicit system dynamics and easy-to-model constraints. Latent space safety filters circumvent this issue by modeling dynamics in the latent space. However, latent safety filters assume RGB provides semantically meaningful information about the dynamical system. This assumption doesn't necessarily hold true for all systems. For reference, our prior toast example. How can we design reliable latent safety filters when RGB partially observes dynamics? Multisafe is one work that pushes on this frontier through uncertainty quantification, where uncertain latent states are just assumed to be unsafe. However, this can lead to overconservativeness and is merely a patch for a more serious problem. Alternatively, we can increase observability through the addition of new data modalities. Beyond theoretically obvious performance gains, we provide the key insight that for many safety-critical tasks, the dynamics and constraints are not visible from RGB alone. The toy example below is a pedagogical system analogous to our toast example we call Dubin's toast. If the blue vehicle passes over the red hot plate, it heats up at a constant rate. We note that the failure is only visible in the RGB channel once the vehicle exits the hot plate, to mimic the visibility of the toast failure only being visible once it's flipped, or off the pan. This provides two concerning limitations. We observe system failure some non-negligible time after it has occurred, and we observe no continuous flow of information or thermodynamics that would enable us to understand why the failure occurs. In the heat channel, it is easy to observe failure, and thus define a set of constraints, for example, a temperature threshold via HJ reachability, and there is also a continuous flow of thermodynamics, which showcases the need for multimodality in situations where RGB alone is not sufficient. We present Multisafe, a multimodal latent safety filter. Our main contribution is on the representation learning side, where we augment the existing world model architecture, Dreamer, and latent safety filters to accommodate for new modalities. We do this through mid-level fusion, where we add an additional encoder and decoder layer for our additional modality, in our case heat, and fuse the latent embeddings together to learn a more semantically representative latent space. The objective of this world model training process remains the same, to minimize the difference between the sampled next observation and the true observation. We train both the recurrent state space model and the classifier at the same time. Though not our contribution, we include the rest of the pipeline for a holistic overview. After learning the classifier, we learn a backward reachable 2, the set of states on which you will inevitably be driven to failure through DDPG, and a corresponding policy through an HJ loss-enforced temporal difference error. During deployment, we employ the filtering technique discussed earlier to obtain the switching control. Our first sanity check makes sure that our method works in the simplest example. We iterate over a grid to obtain a ground truth dynamic programming solution for our 4D Dubin's model, which is a privileged solution that observes heat. We evaluate our method with respect to the ground truth BRT. We fix the angle and initial temperature and compute our BRTs over the grid, where we evaluate two different values of initial heat. We can see that our learned solution is highly similar to the ground truth BRT. In this sanity check, we provide no action for the robotic arm. This allows us to check if we can learn an action-free world model for failure prediction. This sanity check has also proven more difficult to verify. Though we define failure with respect to the thermal input, our learned classifier is not accurate, incurring high false negatives and false positive rates. We are currently investigating this issue, specifically looking at posterior collapse or the influence of RGB as a distractor to the world model learning a proper failure classifier. And of course, this project would not have been approachable to this degree without the help of my co-authors, Ken and Andrea, alongside Google Research for their funding, the entirety of the Intent Lab for their support, and the Robotics Institute Summer Scholars for all the guidance that John Dolan and Rachel Birkin have put together to make this experience valuable.